Kia ora and welcome to video 3 in the series Delightful Differentiation. This video and the problem in it is going to be covered by a former student of mine from 2023, Jay. Jay's at the University of Auckland currently studying art and maths, so a great combination, something that I did through school. I also did art and graphics the whole way through, so he's following his passions there, which is awesome. He had a really good time recording this video, so hopefully you enjoy it. Here's the question that Jay is going to be covering. We've got a function e to the minus x times tan of 2x, and straight away when you look at the graph you can see that it's increasing everywhere, which is kind of weird because it has asymptotes. But we can see here that as we go up, the function keeps going up, it heads off to infinity, and like a good movie, to infinity and beyond. It then comes back from negative infinity, but it's still going up. So this little part of the question where it says show it's increasing within any interval that it's fully defined just means exclude the asymptotes. If you take any section or any interval of x, prove that the function is going up. So as always, give the problem a go before you see the solution, and we'll see you in the next video.
Hello everyone, my name is Jay, and today I'm going to be showing you how to solve this problem, namely which is to show that the equation y equals e to the minus x tan 2x is increasing for all x within any interval a is less than x is less than b that is fully defined. So, first question, how do we know that y is increasing? What is something that tells us that y, the function of y the function is increasing? So y is increasing when dy over dx is equal to 0, is greater than 0. So when the gradient is greater than 0, when the gradient of the function is greater than 0, which means that the function is increasing. So basically what the question is asking you to prove is that dy by dx is always greater than 0, although, well, not always, but for all x, excluding intervals which have an x which is not defined, but we'll get more onto that later. So the way this problem, you just start by finding the derivative of the initial function, and for this we will need to use the product rule, which is that if the product of two functions, if you have two functions fg, the derivative of their product fg prime is equal to f prime of g, not f prime of g, f prime g plus f g prime. So then we can just say that e to the minus x is f and tan of 2x is g, and then we can get dy by dx. Now with e to the minus x, it's kind of an identity that the derivative d by dx of e to the ax, where a is just a constant, is equal to a e to the ax. So you kind of just can bring a down. And since we have e to the minus x here, so this is essentially e to the minus 1 times x, we just bring the minus 1 down. So the derivative of e to the minus x is minus e to the minus x times g, which is tan of 2x. And then we have to add f, which is just e to the minus x, multiplied by g prime. Now for tan 2x, for this one we need to use the chain rule, so we need to find the derivative of the outside and then also of the inside here. So we'll start with the outside. So what's the derivative of tan is just secant squared. So we have secant squared of 2x, and then we have to multiply that by the derivative of the inside. The derivative of 2x is just 2, so just multiply it by 2. So now we have the derivative. And then what we're going to do from here is pretty much just rearrange and rewrite things in order to show that it is always greater than 0, well, apart from the exceptions mentioned in the question. So first off, just to start, we have e to the minus x here and here. so we can just factor that out. So we have this is equal to e to the minus x, 2 sec squared 2x minus tan of 2x. Now we already have something useful because we have e to the minus x out here, and e to the minus x is actually always, oh, that's a very, always greater than 0. This is true of any exponential function. If this bit down here is greater than 0, then the e to the power of anything will always be greater than 0. So now we know that part's greater than 0. We can kind of just ignore it and just focus on this part here and showing that this is always greater than 0. So I'll just bring this down. So we have 2 sec squared 2x minus tan of 2x. Now, in this current form, you can probably do some things with it because there is the relationship between sec and tan. However, if you just what you can do with this is just turn it back from sec and tan into just sine and cos. So if you do that, you just get this is equal to 2 over cos squared 2x minus sine of 2x over cos 2x. And then the next step, just to simplify this a bit, is to make this all one fraction. And the way you do that is by just multiplying sine 2x over cos 2x, just multiply it by cos 2x to get or cos 2x over cos 2x, so you're multiplying it by 1, but it allows you to get the same denominator for both fractions. So then this is equal to 2 minus sine of 2x times cos 2x over cos squared of 2x. Now here we have the second useful thing. We have cos 2x, but it's squared. And what the squared, since it's something squared, it means that this is always greater than or equal to 0. Now the greater than 0 bit is good, but the equal to 0 bit is bad, because that means that if this is equal to 0, it means that this fraction here is undefined, which means that derivative is undefined, and so that we can't say whether the function is increasing or decreasing at this point. However, if we go back up to the initial question, this is where the condition here comes into play, because it says within any interval that x is fully defined. So that means we can exclude all intervals which have an x which makes y not defined. So whatever values of x give a y which is not defined, we can just exclude all those x's, which is great. So if we write the original function down again, y equals e to the minus x tan 2x, when is this function undefined? So e to the minus x, just a exponential function that's always defined for all real values of x. However, tan 2x, this one is undefined at some points, and tan 2x equals sine of 2x over cos 2x, and which means that tan 2x is undefined when this cos 2x is equal to 0, which means that whatever values of x give cos 2x equals 0, we can just ignore all those values, since those values are excluded by the condition in the question. And handily, excluding all values of cos 2x equals 0 also means that we are also making it so that cos squared of 2x, we're excluding all values of that which make that 0, because since cos squared of 2x is equal to 0, I'll just write down, cos squared of 2x equals 0 only if cos of 2x equals 0. But since we're excluding all these points, we are excluding all these points, we are also excluding all these points, which means that cos 2x, we can just say that cos 2x is, we can just say it's greater than 0, because all the points where it is equal to 0 are being excluded. So that three-hand, we have another thing which is always greater than 0. So now we just need to work with this top bit here and show that this bit is always greater than 0. So bring that down, and we have 2 minus sine of 2x times cos of 2x. And something you might notice about this, that's very similar to a common trig identity, which is the double angle identity for sine, which is that sine of 2 theta equals 2 times sine theta cos theta. And then what we can just do with this is we can just divide both sides by 2, and we get that sine theta over 2 equals sine theta cos theta. Now this means that we can change this, and then this is equal to 2 minus sine of, not what, oh, sine of 4x over 2. Now since this is a double angle formula, then we start, it takes theta to 2 theta. We're starting with 2x, it goes to 4x. And then now, just to make this a bit simpler, we can make it into a single fraction. So just multiply this by 2 over 2. And we get that 4 minus sine of 4x is over 2, or just 4 minus sine of 4x over 2. And now this is pretty much like the last part. So 2, that's good, that's greater than 0, we know that. Or we should know that. And then we have this bit here. So what do we know about sine of 4x? So 4x, sine of 4x is a sine. It's a sine function. So we have that, so it is bounded by 1 and minus 1. So sine of 4x is, no matter what x is always, not between, but is from minus 1 to 1. So that means then that 4 minus sine of 4x, since sine of 4x is between minus 1 and 1, 4 minus sine of 4x is between 3 and 5, which means that this is also always greater than 0. So now we have shown that all parts of the derivative are greater than 0, and I'm just going to write the full derivative back down here. I'm just going to read it from my notes since I don't want to have to go back up through my working. So it's 4 minus sine of 4x over 2 cos squared 2x. Yeah, there we go. Equal, that's very small equal sign. So what we've done is we've shown that this is always greater than 0, this is always greater than 0, this is always greater than 0, and this is always greater than 0. And since all parts of dy by dx are greater than 0, that are always greater than 0, well, always for all x's relevant to this question, we can say that dy by dx is greater than 0. I can say for all relevant x. Just because it's not for all x, it's just for all x's that are relevant to this question. So since dy by dx is greater than 0, that means, therefore, y is increasing. And then you probably want to write something down under, just continue write something here about, you know, the condition you have up the top, which excludes all x's where y is not defined. So for all intervals where y is defined, fully defined, this is true. So yeah, that's the answer. That's the solution to the problem. You're done? Yeah, well done.